Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture number 4, and we are in video 11. And we are continuing our discussion about maximum likelihood estimators and then moment of method estimators, which we won't get to in this particular video. So last time we reviewed the properties and of expectation, covariance, and variance. This time we're going to get into something called the likelihood function. We're going to talk about maximum likelihood estimators and maybe even get to the properties of logarithms, but we'll have to see. All right, so let's get started. So after our review, we're going to now start with point estimation. So there's two methods that we're going to study for estimating population parameters. And these are both very important, and you'll see the MLE more often than you see MME. So we'll see some reasons for that as we do some examples. So here's what the procedure is. We're going to take a random sample from whatever the distribution is. So that's one way to think of it, taking a random sample. And when you take a random sample, you're going to be tempted to say the data. So am I. But really, we're talking about random variables. So we're going to observe the random variables, and these are going to result in values. So results in actual values, x1, x2, up to xn. Now, the numbers 1, 2, up to n just denote the order in which the values were observed. So, because they correspond to the first random variable, the second random variable, up to the nth random variable. And we're doing those in that order, but that doesn't mean that we're going to have ordered values, smallest to largest, by any means. They're random, so they're going to be fluctuating from value to value. Okay? The other way that we can look at this is we can say that we're going to repeat an experiment in independent times. So this takes us back to things like the binomial distribution, where we have independent Bernoulli random variables, and we repeat the trial or the experiment over and over again. Okay, and those repeats are independent of each other, like rolling a die. The outcome of the previous doesn't affect the outcome of the next, so they're independent. And what we're going to do is we're going to use the results from these random variables to estimate a population parameter, and to give it a generic parameter value, we're using theta. Okay. So again, this is an upper level course. You're a professional statistician, so to speak, not certified, but a statistician after you graduate, and we need to use the proper language so that people know that we know what we're doing. Okay, so theta is the name of that Greek letter. And again, we're going to use the actual observations or values or results. Okay, so a statistic is an estimator of a population parameters, and it's a function of the independent random variables involved, and there's n of them in this case. So we're saying that it's u of x1, x2. Notice these are random variables. These are the capital letters, not the little letters, because a function of constants is not very interesting, but a function of variables is. Okay, so this function stands for whatever we're going to do to these values. All right, but it's a function of the random variable, not a function of the observations. Okay, observed values, function of the random variable. All right, so because each time we calculate this, we're going to get a different, or each time we take a new random sample, we're going to get different observations, and thus probably have a different value of our estimator, theta hat. Okay, so theta hat is a common symbol for an estimator. Now, some people use theta tilde, and so we are going to, so the book uses theta hat for the MLE and theta tilde for the MME. Some books just use theta hat and you'll see me go theta hat MLE, and sometimes you might see me go theta hat MME. But sometimes this notation is not very easy to work with. Let's say we're using sigma squared, and so we say sigma hat squared 1, and then I'm supposed to put MLE down here. That doesn't work too well. So we have to be careful with our notation, not to make it too complicated. So I'll try to follow what the book does whenever I can remember. Okay, so we want the computed estimate theta hat. Remember that, so how we're computing it is using the actual values. But the statistic is a function of the random variable we're plugging in. So we could rewrite this as u of x1 equals little x1, x2 equals little x2, up to xn equals little xn. So just like we did with probability. Okay? So this is a shortcut notation, but I know that these may seem different, but this is the reason that we're actually putting the equals value, and then we're being a little sloppy and just putting these and saying we know that these values correspond to the appropriate random variable. Okay? So I'm saying this because I know students get confused about it, and I'd like to try to clear that up for you so that you don't get confused. You may think that your professor is being sloppy if you're taking somebody else for this, but they're not. This is standard practice. They assume that you know that little x1 is a result of capital X1, okay, the random variable. So I hope that helps some of you. Okay, so we want this computed estimate, this theta hat, to be close to the actual real value of theta, which we do not know. So theta hat is called a point estimate, and it's a point estimate because if we plot it, it's just going to be a single point on the line. I guess I should probably put that underneath the number line. Theta hat, okay? So theta hat is that value, and we could call this x if that's our random variable. Okay. So the likelihood function, what is this? So let's give a definition and see if we can understand from this. Let x1 to xn be a random sample from a population, or you could say from a distribution. These two things are equivalent. They mean the same thing. If you say it's from a distribution, you mean it's a population with that distribution. Okay. So with a PMF or PDF, it can be discrete or it can be continuous. Okay? So, and remember that when we talk about the PDF and PMF, we're talking about the random variables. But we're going to flip that, and we're interested in the estimates of the parameters, not the data. So let's take a look at this. So we can rewrite the PMF or PDF as f of x, and then semicolon, and then however many parameters we have, theta 1, theta 2, up to theta k. Okay? Where theta 1, theta 2, up to theta k takes a set, takes values in the set capital sigma, which is the parameter space. Theta I equals 1 to n, are our parameters. Okay? Each theta I is a parameter. So theta 1 is a parameter, theta 2 is a different parameter, etc. Okay? Because x1 to xn are IID, they have exactly the same PMF or PDF. The joint PDF or PMF is given by the product, right? So if they're independent, then we can calculate the likelihood function, or the joint PDF, if you would, by just multiplying the individual PMFs or PDFs, okay? So remember, if they're not independent, then we have to use conditional probability. It becomes, you can do it, but it becomes a lot messier than this, okay? So, and you have to be able to figure out more, you usually have to be able to figure out those conditional probabilities somehow with the data. Okay, so here I have x1, and then theta 1 to theta k. Here I have x2, theta 1 to theta k, all the way up to xn, theta 1 to theta k. And again, theta 1 to theta k are in the set sigma, the parameter space. Okay? And when we view it as a function of the thetas, the parameters, we call it the likelihood function. So it's a joint PDF or PMF, but we're not going to use x as the variable. We're going to use the parameters as a variable. We want to find them. That's what we're interested in. We want to find the best parameter that we can to estimate, or best estimate of the parameters that we can using the random sample. Okay. So now there's another way to write this, and sometimes more archaic ways is to make this bold. Another archaic way that you'll see is where they put a squiggly line underneath the parameter, the value to say that it's a vector or a matrix. Okay, but the book and more modern technique says you should be able to figure this out based on context. So now I'm just going to define it. Theta is equal to this vector of parameters. Then we can write this as the likelihood function, and this is the most common way that you see it. So it could work for just one theta or a bunch of thetas, okay? Which may seem confusing to you, but that's the convention. So the L of theta is going to be the product of f of xi and theta, okay? So that's going to give me f of x1 theta, f of x2 and theta, up to f of xn and theta, okay? And the value of theta that maximizes this is theta hat, and is called the MLE, or maximum likelihood estimator, okay? So, first thing we need to know is if theta is a scalar quantity, that means there's only one parameter. Then theta hat is simply a function of the observed values. Remember that these go with the random variables. Okay, so to calculate it, you're going to use the actual results, the actual observed values to get this. That's all we can do. And this is a single function of x1, x2 up to xn. Okay? And we should probably say capital X1, X2 up to xn. Okay. If theta is a vector, say theta 1 to theta k of dimension k, then the MLE theta hat is now the vector and of dimension k, and theta I is a function of x1 to xk random variables, and where I is 1 to k. So we have one of these for each of the parameters. Let's do an example. This is example 1. Now, not only are we using a discrete distribution, but more importantly, because that's really not important for MLEs that much, okay, whether it's a discrete or continuous, what's important is whether the parameter is discrete or continuous. So we're going to see that we're going to use a discrete case for the parameter. Jumping down to here. 0.2, 0.7, and 0.9, we're going to limit the possible choices to that. That sometimes happens in real life, that maybe that's the only possible choices for some reason, and we want to, we don't need to look at anything else. We just need to know which one of these values maximizes our likelihood function, and thus maximizes the probability of occurrence, and thus is the value that should be our maximum likelihood estimator. So we have a random sample, x1 to xn. That means that they're going to be IID, independent and identically distributed. All right? And they're Bernoulli random variables. And I want to remind you that a Bernoulli random variable is simply a binomial random variable with n equals 1. You plug in 1 for n, and you have, so that means you don't have to, remember another separate distribution. If you can remember that the Bernoulli is simply a binomial with n equals 1. So I can write the PMF of x as f of x, but I'm going to write it with respect to p as well, because p is going to be the function that we want to, or the parameter we want to maximize. So we're going to consider this as a function of p. And remember that p normally is between 0 and 1, but we're limiting that, the parameter space here, to 3 values. So when I plug in n choose x, p to the x, 1 minus p to the n minus x, when n is 1, then n choose x is 1. So this will be 1 choose either 0 or 1. In both cases, this is 1. So this term goes away to 1. And then I have p to the x, 1 minus p to the n is 1, 1 minus x. That's exactly what I have here. And don't forget your support. X is only 0 or 1. Okay? This is very important when we solve this problem for the continuous case. Okay. All right. So the parameter space, again, we're limiting it to 0.2, 0.7, 0.9. The first part of this example is find the likelihood function. So for A, L of P is a function of P. And since these are IID, which is, I think, the only case we're going to deal with in this course, because usually it's a more advanced course when we don't consider it a random sample or independent observations. So this makes it easy. We're always going to take the product in this course, I equals 1 to n, of f of x, I, p. Remember, there's n of these xi's, x1, x2, up to xn. And so this is the product from I equals 1 to n of, not f, of p to the xi, 1 minus p to the 1 minus xi, and this is equal to p to the x1, 1 minus p to the x1, or 1 minus x1, times p to the x2, 1 minus p to the 1 minus x2, dot, 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 all the way up to p to the xn, 1 minus p to the 1 minus xn. Sorry, I'm running off the page there. Well, if I just look at the p's, remember the p is the same value. I don't have any indices on p. So this is p to the x1 times p to the x2 times p to the x3, however many n is, up to p times x to the n. So I add the exponents. This is going to equal p to the sum of xi. Now, I look at the term 1 minus p. Again, 1 minus p is the same value for all of these. So I multiply them, so I need to add their exponents. I'm going to end up with 1 minus x1 plus 1 minus x2 plus all the way up to 1 minus xn. There are n of these terms. So there's n of these. So if I have n and I add it, or I have 1 and I add it n times, that's going to be n of them. So this is going to be 1 minus p to the n, and then I have minus x1 minus x2 minus xn, or I could say plus the negative of that, right? So it's minus the sum, again, of xi, and we need to say that p is in sigma. All right. Okay. Now, here I have a discrete case. And if you look at part B here, we say find the MLE of p hat, or the MLE p hat of p if n is equal to 5 and sum of xi is equal to 3. So for B, we say that L of p is equal to p, and sum of xi is 3, so we substitute that in, 1 minus p, and n is 5, and then sum of xi is 3, and so this becomes p cubed 1 minus p squared. Okay? And p is in 0.2, 0.7, or 0.9. Okay? So that's our likelihood function. We need to maximize this. Since it's discrete, all we have to do is we have to say value of p, and then we want L of p. Okay? So when p is 0.2, okay, then we have 0.2 cubed, 1 minus 0.2 is 0.8 squared. And when it's 0.7, we have 0.7 cubed, 0.3 squared. When it's 0.9, we have 0.9 cubed and 0.1 squared. This is equal to 0.00512. This is equal to 0.03087, and this is equal to 0.00729. Okay, so 245, 245, yeah. So this is the largest. So our MLE, so p hat equals 0.7 is our MLE in this case. So this is actually the simplest case. Many books don't go over this case, and that's a problem for students. They think that it's so easy that students will be able to do it, but they're thinking so hard that it's going to be continuous, that they do derivatives and everything, and you really can't solve this problem that way. So, or there's no need to take derivatives. So we have solved part B. That's it for this video. Please make sure you update your formula sheet. If you have questions, come to virtual office hours. If you can't wait, email me. I'll get back to you as soon as I can. And we hope you stay safe and see you next time.